This begins the EE555 discussion on Wednesday, February 26, 2014.
Good morning, everybody. Let's get started. Today we'll talk about TCP. We'll see some problems that you might be familiar with. Excuse me. Before that, I wanted to make an announcement to ask, basically, if you know somebody with the name Mansa Zhang. No. Anyway, the problem is that there are some people that contact mailbox full, which means that I cannot respond to them. Okay? So whenever I respond back to them, it comes back to me saying, you know, over quota. So there is no way you can communicate with these people. So if you know somebody, or talk to your colleagues and make sure everybody has a non-full mailbox and receive emails. All right? And there is a way for that. There is a way, if you don't know, to set up your Google email to access to. So your US email will be forwarded to a Google account which has maybe 20 gigabytes of quota. Make sense? All right, so do it if you haven't done that. So let's see the first problem. Problem number 1, congestion control algorithm that uses linear increase and multiplicative decrease but not slow start in units of packets rather than bytes, and that starts each connection with a congestion window equal to 1 packet. Of this algorithm, assume that the delay is latency only and that when a group of packets is sent, acknowledgement is returned. Plot the congestion window as a function of a situation in which the following packets are lost. Packet number 9, 25, 30, 38, and 50. Simplicity, assume a perfect timeout mechanism that detects a lost packet exactly 1 RTT after it is transmitted. You might be familiar with this problem from 450, but let's see it again. Do you understand the problem? We have a TCP congestion control algorithm. We lose some, and we want to see what's happening exactly. Meaning we want to plot for every time instance. We want to find the congestion window and then give a plot of that. All right, so let's get started with that. Let me put that here. So we have that. First of all, let's write down the packets that are. This is number 9, 25, 38, and 50. We will build a table for every RTT, and then you can use that. So we have RTT. We represent CWND. That's a standard. We have how many packets are sent in this particular RTT period. All right, so first of all, we have RTT number 1. There are many ways to make this plot. Not many, I mean, there are a few ways to make this plot depending on how you define your x-axis. Some people or some books start from 0, some others start 1, depending on what assumptions they make. Do you remember from 4 what's like the logic behind each of these? Basically, some people the time as the time as a continuum, and then they start from 0 to 1. This is RTT1. From 1 to 2, this is RTT, and this type of thing, right? And there are some other people that say, okay, RTT1, just a point, and I give the first congestion window. Or the problem is that sometimes we begin of the RTT, or some other times what's happening at the end of the RTT. Just make some assumption, be clear, and everything else is fine. It's going to have the same shape, but it might be shifted a bit. Okay? For RTT1, what is the congestion window? It's given that it's at 1, right? It starts its connection with a congestion window equal to 1 packet. So that's given. What does that in the first RTT period, at the beginning, better, we're going to send one. After one RTT, we will know if we are good or not to continue, right? We get an acknowledgement, everything increase the congestion window by how much? By 1. Sounds. We send packet number 1. Those are packet numbers over here. 2, congestion window. You understand the logic, right? After one RTT, we are acknowledgement, we increase the congestion window by 1. So we will do, and this allows us to send which packets? 2 and 3. At RTT number 3, we have 3. The first packet load 9, we can go like this. So we will send packets number 4 to 4, 5, 6. RTT number 4, then we have congestion window is 4, we increase, additive increase, linear increase, and then we have which packets? 7 to 7 plus 3 basically, yeah? So it's 7 plus this guy minus 1, because we, however, what's happening over here? We have a loss. This is packet number 9. Okay? How the algorithm will react in this case. Any ideas? Louder? Somebody? It's going to have the window. What packets will be retransmitted? 7 to 10? Who says 7 to 10? And how many people say and above? Only one acknowledgement, but we didn't assume that the acknowledgement corresponds to one packet. We assume here, and that, pay attention to the sizes, we can assume that the acknowledgement is cumulative, which means it's going to acknowledge the last packet received, so after that we can transmit whatever is lost. Make sense? So in this case, where is that? It is returned. We can call it cumulative. That's a standard TCP acknowledgement. Make sense? All right, so this means that only above will be transmitted in the next slot. So RTT number 5, so the congestion window becomes 4 divided by 2 equals 2, and then we need to RTT number 6, keep going, again, right? And then we send 3 more. We have space till 25. 11, 2, plus 2, to 13. It's also 7 here. Everything is normal. I keep going. Congestion, the previous plus 1 means 4. And here we will transmit 14 plus 3, 17. So far, so good, right? Okay. So, RTT. If you want, let me know, guys. RTT number 8. What happens over here? We just go from 4 to 5. And transmit packets 18 plus 4, 22. Right? And then we go to RT9. Still we are good. We don't have any loss. The lost packet, the next lost segment is, so we will transmit 6 packets, and this means we will transmit packets 23 to 28. And from this bucket over here, we will lose packet 25. Which means what? What happens in our half. First of all, congestion window will be 3, and then we will transmit same 25 and above, right? 3 packets from 25 and above, which means 25 to 10. RTT 11, you have any loss here? No. Till 30 we are good, which is the next loss. So congestion window will be 4. Packet sent is going to be plus 3, will be 31. But again here we have a loss. 30 is lost. Packet 30. Which means that congestion window at RTT 12 will be half. And this means also that we will transmit 30 and 31. RTT number 13 till 38, this means we have 3, and this means we transmit 32 till 34. Let me write down one more. 34 we are good, congestion 4, so we transmit 35 till 38. 38. Do you follow? Right? So we continue the last bunch of packets. Sorry, packets sent. We have RTT 15. A congestion window becomes what? We have a loss here. It's going to be 2. And then transmit 38 to 39. 16, congestion window increased by 1, and then we will transmit 4. Alright, and then congestion window becomes 4, and we will transmit the next packet lost. To keep going, it's 43 plus 3, 46. RTT 18, congestion window becomes 5. We will transmit 47 plus 4, 51. Okay? This over here was packet number 50. Alright, so what does this mean for us? We go at RTT 19. What is the congestion window? We choose basically, okay? What kind of, we divide by 2 and we take the floor. The smaller integer, right? In other exercises given, you can ask, of course. Assume that this happens. We divide, okay? So this will become 2, and which means that we transmit 50, which is the lost packet, and 51, and that's it. Then we can continue. All right? So that's how the algorithm evolves. Now, what you need to do over here is you can make your own plot at home using Excel maybe or whatever you want, and just plot these points, plot a congestion window against RTT. If you want to play around with a different, rearrange the points, you know, from 0 to 1 or the way you want, starting from 0, starting from 1. Okay? It starts from 1. Professor's notes start from 0. Choose. Any questions? All right, so continue. All right, so this is the second problem on TCP. We will refer to this figure over here. I'm showing just to have an idea what I'm referring to. We have the congestion window size for a TCP transmission, and we will assume both TCP Tahoe and one is Reno, and we will see what happens in each case. Okay, we'll answer this graph. So the question is that this might correspond to not both. Basically, this is Reno. The main assumption is we'll say, oh, if it's Tahoe, what happens? So let's go read the problem statement. Consider the showed you, assuming TCP Reno is the protocol experiencing the behavior shown in the figure, answer the following questions. You should provide a short discussion justifying your answer. First question, identify the intervals TCP slow start is operating. Let's go one by one better. We're going to save time. So we need to write down the solution here. So slow start over here. Any ideas? In this graph, in which time interval? First of all, I added the y here to make sure that we all agree that this is 32 and not 33 or 40, you know, and so forth. So let's use these values, but now we don't use these values. We need just the x coordinates, the time. We need to find what is the slow start phase in this graph. Identify the intervals of time start is operating. Do you remember from TCP what you learned in the previous week? Slow start starts from 1. It's the phase that we double basically the congestion window. And this, how does this happen in reality? For each acknowledgement, we increase the window by 1, right? So if we send 2 packets and we get 2 acknowledgements back, we'll increase for each acknowledgement the congestion window by, so 4. Sorry, we send 2 plus 1 for the first, plus 1 for the second. That's why we double. Okay? So slow start in this case will be from 1 to 6 is from, that's a good, sorry, those are not, those are congestion avoidance, right? We'll see that. This is 23 to 26. Okay, so let's write down this. I'm just writing the answer. 23 to 26. All right. The second question is identify the interval TCP congestion avoidance is operating. I think I gave you the answer previously. So congestion avoidance is which area? The area where we slow down, right? We slow down to a linear increase over here from 6 to, very good, and from 17.
The time is 19 o'clock.
Till 20, perfect. So we have 6 to 60, and the other area is 17 to 22. Do you agree? Next question is, after the 16th transmission round, is segment loss detected by a triple duplicate ACK or by timeout? After 16th is over here. Here, do we have a triple ACK or a timeout? Do you remember the difference? Triple acknowledgement. No. Why? Not. I'm not asking why it happens. How is why you say it's triple ACK and not timeout, given the graph here? Perfect. Yes. So the congestion window goes to half. Don't start from 1. Okay, which is the reaction if we detect a timeout. All right. That's the answer. C. 3 duplicate ACK. Otherwise, congestion window would 1. Let's see. Next question is D. After the 22nd transmission round, is segment by a triple duplicate ACK or by timeout? After the 22nd here. Same reason, timeout. Timeout because congestion window equals 1. All right. Question number E. What is the initial value of at the first transmission round? At the first transmission round. How do we detect? Why is 32? Perfect. So the thing is that SS threshold is used in order for the TCP congestion control algorithm to become, after we pass the threshold, we just change to congestion avoidance phase, which means linear. So at that point, over here, this is the SS threshold at the beginning. Time instant the SS threshold, right? We update it when? Yes, we have a loss, right? Or a timeout or a duplicate tag. That's when, like when we go down. Okay, so let's write down the answer. 30, you go from slow start to congestion avoidance. Right? Now, what else? F. What is the value of SS threshold at the 18th transmission round? By the way, over here we are talking about downs. That's why we start from 1. Okay? Just to give you from 1. And not from 0. What is the value of threshold at transmission? 18th is here. 18th is at the second point of the linear increase. This is threshold in this case 21, and can you give me a perfect, and we set this as threshold, half the perfect. So the congestion window before the loss was, after we go down, we have the congestion window and we set the SS threshold equal to before the loss, right? So over here, congestion window at time 16, I just put it in a parenthesis as a argument, 16 over here, over, that's 42 divided by 2, which gives 21. Okay? This is SS threshold. No, we don't take the half of the original. We take all that was over here, for example. I'll just give you an example. This is the FSM. This is the FSM of the TCP congestion control. Maybe not. Depending on which phase you are, it tells you exactly what the algorithm says to the value. So we were in dance, and we have here duplicate. SS threshold is congestion window by 2 and congestion window plus 3 MSS. Now, this 3 MSS is a different story that QoS doesn't follow, but let's not talk about that, okay? But the SS threshold, what we do is we divide it by 2. You agree? All right, so actually, no, it follows. No, I take it back. QoS is a good guy. Okay, so I confused that with another problem because problems that these authors have, they are not very, punctual. Okay, so we were here in question number, got lost. Did I answer your question? Okay. So we go to G, what is the value of SS threshold at the 24th transmission? 24th is here. 24, how much? 14, perfect. We go 29 divided by 2 floor. Why floor? Because it's given, I think, or not? No, it's not given, but that's the, right? So before the loss, we want to find the SS threshold at 24th over here. The threshold here will be the same as here. So how much was here the congestion window? The same happens. We divide by 2 and we take the floor if it's not an integer. 29 divided by 2, floor, which is 14. So let's write this down. Congestion window 2 divided by 2, this is equal to 29 divided by, which is 14. And during what transmission round is the 17th segment sent? That's annoying. All the, for all the RTTs, how many packets did we send? Right, so during what transmission round we need to find where did we send packet 17, which means we will see how many packets we send. Basically, not even how many, which packet numbers number 1, then 2, 3, 4, 5, 6, 7, and so on and so forth, till we reach 70, okay? That's what we'll do. Do you have a number? I'm going to take it from the screen. I need to write down the full answer. Okay, so what's this? Round number, congestion window, packet sent. I'm just creating a convenience. So round number 1, how many packets? Congestion window is 1. 2, we send, congestion window becomes 2, and packets 2, 3. Round number 3, what is the congestion window? We have slow start phase, that's why, right? So we send packets from +3, 7. 4, congestion windows becomes 8. To help you over here, round 6 we are good, we are doubling, okay? So we send 8 plus 7, 15. Round number 5, congestion window becomes 16, and we send packet number 16 plus 15 to 31. And at 6, that's the happy, the window is doubled. This becomes 32, so we send plus 31, 63. Do you agree? Till here we double. So what happens at 7? So the window over here, 33. The previous plus 1. And over here we will transmit what? 4 till 96. That's it. The answer is that 70th segment is transmitted in the 7th, right? All right, good. So let's see. Any questions? Okay. Next question is question I. Assuming a packet loss is detected after the 26th round of a triple duplicate ACK, what will be the values of the congestion window size and of SS 26th over here? Assume that we got triple duplicate ACK. What will be the values of congestion window and SS threshold? All right. So over here it was 8. So what happens? This is question number I. Who wants to? As a threshold, what happens is the congestion window divided by 2, right? So it will become 4, right? Okay. For the other question, I'm sorry, we need the graph I sent you, I guess, which is, we need the graph I showed you, not sent you. Over here. We are at start phase. We are at slow start phase, right? We detect M3 tracks is this arrow. So we go to fast recovery, the threshold, half the window size, and the congestion window becomes the threshold plus, okay? Yep. Let's put this out here. So I'm writing SS threshold equals at time 26 divided by 2. This is 8 over 2, which is 4, and window at time 22, I'm just leaving it like this, is equal to SS threshold equals 7. All right. Continue to question J. Suppose TCP Tahoe is used instead of TCP Reno and assume the ACKs are received at the 16th round. Triple duplicate ACKs are received over here. Over here. All right? And the congestion window size at the 17th round, meaning how the algorithm reacts in this. So what is the difference between the two when it comes to reaction to ACKs, duplicate ACKs? And when we have a duplicate ACK, what is the reaction of the Reno? Halves the right? All right? So what happens in the case of Tahoe? It starts from 1 difference, right? So yes, so let's write this down as a threshold equals congestion window at 16 divided by 2. This is 42 by 2 equals 21. And the congestion window goes to 1. That's the behavior of TCP Tahoe when triple duplicate ACK happens. And be careful over here. I don't know if I'm saying it differently just because of speed. Congestion window is different than SS threshold, we said, right? I'm repeating it. SS threshold is halved, take it, by 2, and congestion window is half plus 3, right? In general case we're seeing over here. If I forgot to say the plus 3, so when 3 over here, for example. Okay, make sense? Question K. Question K is over here. I'll go to read of one page. Again, suppose TCP Tahoe is used and there is a timeout event at the round. 22nd is here, timeout. How many packets have been sent out from 17th round till the 20th inclusive? 17th is this, from here to this line. Let's see. So I'm going to make a quick table and congestion window. We don't care about packet numbers here, we care about how many. So 17, we are talking about Tahoe, remember. Tahoe congestion window starts from 1, right? So, and what kind of phase? It's congestion avoidance, right? So it will be, is it? No, I'm sorry. It's not, right? It's going to be slow start. So 17 with window 1, 18, 2, 19, 4, 20 we have 8, 21, 22, we need something, we need this guy over here, right? We were doing slow start and we reached the threshold, so we have to continue linear. Do you agree? So over here, sorry, we will have 21 and not 30 congestion window. Do you agree? Okay. So why is that? Because we just found previously what the SS threshold will be. So in such a case, how many packets send total? In total is 52. If you add them up, 52. Any questions? Do you agree? Okay, I know the only tricky problem here, or I don't know if a problem, but is that the TCP has a few, details and variation of TCP version to the other. So make sure you review this chart. This is from QoS and ROS. From those that are 450, you know what I'm talking about. And also the professor gave you, I guess, similar information in bullet to read. Make sure you go over it and you remember the basics, okay? I'll post that, by the way. And let's see the last problem. So for the, which is another boring problem, I'm kidding. What is that? So let's see what we have. Problem, consider a simplified TCP additive increase, multiplicative decrease algorithm where the congestion window is number of segments, not in bytes. In additive increase, the congestion window increased by 1 segment in each RTT. In multiplicative decrease, the congestion window size decreased by half if the result is not an integer, round down integer. Okay? Suppose that two TCP connections C1 and C2 share a single congestion of speed 30 segments per second. Assume both C1 and C2 are in the congestion avoidance phase. The connection C1's RTT is 100 milliseconds and connection C2's is 200 milliseconds. Assume that when the data rate in the link speed, all TCP connections experience data segment loss. So when we have speed of the link or more, theoretically, we are losing the packets. All right, that's one. If both C1 and C2 at time T0 have 10 segments, that's given, what are their congestion window sizes after 22? If we start from 10, what is going to happen in 200 milliseconds? And also in the long run, will these two connections get the same share of the congested link? And give an explanation for that. So
5-minute warning, just a heads up.
Thank you. So what happens over here? The solution over here is creating a huge table. I'm not going to draw it here, and we will go over it now. All right? So note is that the RTT of the first connection is half the RTT of the second connection. It means that the first connection will react faster to any packet losses or anything that happens. Okay? So we expect the throughput of the first connection will be higher, maybe double, than of the second connection. Okay? So we want to kind of show that behavior using a table that shows for each RTT what happens. All right, one thing. And the other thing we need, this, when data rate in all TCP connections experience data loss. So whenever we experience data loss, we will have the window. It's given, right? AIMD. Make sense? So, what happens we need to think also of another detail. One, the first connection uses a time window of 100, second a time window of 200. So the logic is, a very rough use is that the algorithm, in order to make a decision what we'll do with a congestion window, is how many packets on average were transmitted in the last time window, and if this is more the line rate, we say we experience loss, so for sure we will have the window size. So connection 1 calculates for the last 100 milliseconds what happened. So it calculates the average. If it's more than 30, we have the window, right? Same for connection is operated in a 200 millisecond window, double. So this is where the first connection show that a congestion is happening and half decrease the window size, but the other no, because it has a to calculate the average. So the fluctuation might be smoother. So we might see a case decrease in the first connection, but not decrease in the other. That's all we need to explain what's. So let's see the table. I'm going to explain to you the high level, not the high level, but the table is derived, and you can look at that, very carefully at home. It's very simple. We break the time into the smaller time scale we have, which is the RTT of connection 2, with connection 1. From 0 to 100. At time 0, the window size is 10, it's given. Everybody has 10. 10 congestion window size for connection 2 as well. What is the average data sending? It's the congestion window divided by RTT. So we will send 100 segments per second. And in the second case, we'll send 50 per second. Smaller RTT, faster, higher throughput. Make sense? Okay. So after 100 milliseconds, the first algorithm, the first connection will calculate how many packets on average it sent. I mean, it happened exactly, but like the God's eye, sees what happened. The algorithm sees. But to predict what happens, we know both connections, what they have sent, so we can see. The first guy sent 100 packets, the second sent 50, and those are averages. The average for this guy that this guy sees is 150, and this it's more than the 30, right? So we will lower the window to 5. Make sense? So, and then with window 5, what is the throughput here? What is data sending? It's 50. This guy keeps the previous window size because the window for this doesn't change anything. So it continues for another 50. Okay. Now, the first guy will do the same calculations. How many we send? We send 150, again above. We lower the window size to the lower integer, divide by 2, so it by 2. 2.5 floor equals 2. With this window size, we will send 20 packets per second. If you understand what I'm saying now, we can stop here because everything else is the same. So this guy will calculate over the 200.
I'm out of time. Yeah.
Thanks. We'll just a few seconds to finish. He will calculate the average in the 200 millisecond window, which is what is the average over here? It's 100 plus 50 divided by 2. This is the average rate of the first connection. 100 plus 50 divided by 2, and the other connection has what? 50 plus 50 divided by 2. 200, which is above what we allow, which means 25. Which means half the window. We make it 5. You understand? So this guy performs this and of this, adds them up and see how much data we send, and that's how we decide what the... Okay, we'll continue this. It's exactly the same logic till then. And to answer the last question, if the log run, will these connections get the same share of the bandwidth? The answer is no, and the reason is that you will see periodicities over here, periodicity here. You see 1, 2, 3, 1, 2, 3 in the congestion window of the second connection. I has its own 1, 2, 3 in a smaller period. You know, it repeats the window. So if you calculate for a period like this, from 1400, let's say, to 100, this guy sends double the packets of this guy. This guy sends double the packets of the second. So this shows that they don't get the same bandwidth. We're going to close here.
And this concludes EE 555 discussion on Wednesday, February 26, 2014.